Atomic theory is an interesting developing story. It's one that's changed throughout time and is very fragmented into many different pieces. The concept of the atom has changed multiple times over the ages. And so really when we talk about atomic theory, we're talking about the development of the idea of the atom. And the atom has changed, like I said, many times throughout its history. The first person to really start talking about the atom was a guy by the name of Democritus. And he lived a long, long time ago in ancient Greece. Now, Democritus and his compatriot here, Aristotle, were thinkers. They were philosophers. And the idea of the atom to them was something very different than the way we would think about an atom today. These two were actually rival thinkers. Democritus developed the idea of atom, or tiny particles, from the Greek for atomos. And he actually believed that everything, every substance on the earth, was composed of atoms. And in that regard, he was absolutely correct, thousands of years before our time. Where he was incorrect, though, is he actually pictured that each atom of any material will be made up of tiny little small spherical shapes of that object. For example, a pen would be made up of tiny, tiny little pen atoms, and an elephant would be made up of tiny, tiny little elephant particles. Aristotle disagreed with this thought altogether. And so again, to summarize, Democritus said everything is made up of tiny particles. Tiny particles. And those tiny particles were just smaller versions of what you all already saw. On the other hand, Aristotle, very much a celebrity of the day, believed in the four fundamentals. And the four fundamentals completely spit in the face of what Democritus is trying to say. He believed in fire, air, water, and earth. And it was because Aristotle's name was so much greater than that of Democritus that the idea of the atom actually disappeared for almost 2,000 years. The idea of the atom was revived by an English school teacher by the name of John Dalton. And he believed in four fundamental things when it came to the atoms. And his postulates, his tenets, well, that each element, or all elements, are composed of tiny fundamental building blocks. Made of atom building blocks. Dalton also believed that all these tiny building blocks were made of extremely small particles called atoms. The third tenet is that atoms of an element are not changed into atoms of a different element by chemical reactions. You can neither create nor destroy atoms in a chemical reaction. And a fourth postulate is that he said that all atoms of a given element are identical to one another in mass and other properties. But the atoms of one element are different from elemental atoms of another. So all atoms of the same element are identical. Some of these postulates were proven correct over the ages, while others were proven incorrect. We'll talk about those down the road. Now, another implication of Dalton's idea, his atomic theory, is we had to start writing things in new ways. He was of the belief that when two things combined together chemically, they created a new substance. Now, unlike Aristotle, though, where you have a combination of, say, earth and water to make a new substance, mud, what he saw is that they chemically combined, yet they still retained themselves in the process. There were still hints of them left behind. So a new language had to be devised. Now, when we talk about carbon dioxide over here, we're talking about one carbon atom and two oxygen atoms. Now, a new language had to be invented, like I said here, And that language including a numbering system. This number down here is called a subscript. And rather than having to memorize the different combinations that make everything around us, this new chemical language was invented instead. So this language says that we have one carbon atom and two oxygen atoms. Over here on the right, though, we have a new introduction. We retained the subscript right here, but we also have a big number in the front. This big number in the front is called a coefficient. And the coefficient acts the same as it does in math as a multiplier for the entire product. So if we have two H2Os, we have a total of 4 hydrogen atoms, and we have a total of 2 oxygen atoms. In 1897, somebody else came along with some new thoughts. And the new thoughts were by a guy by the name of J.J. Thompson. Not Thompson, Thompson. In 1897, Thompson was using a device called a cathode ray tube. This cathode ray tube was created by a guy by the name of Sir William Crookes and actually forms what you guys have maybe noticed in old computer monitors or TVs. The basic idea is that an electrical signal is sent through a series of magnets. Now, when Thompson was using this in the dark, he noticed a steady stream of small particles that were attracted to a negative plate. And because they were attracted to this negative plate over here on this end, he postulated that they must have a negative charge. Their mass was very, very small and actually unmeasurable to him. And he devised the name electrons because the electricity was flowing through it. He had discovered the first of the 3 subatomic particles. Now with that, he had to devise a new model. Up until that point, the standard model that was accepted was that of a spherical billiard ball. And that spherical billiard ball was solid all the way throughout. So imagine the cue ball on a table. Now with the introduction of the electron, something that was negatively charged, the idea of the model had to change. And so what J.J. Thompson postulated is that these tiny little electrons were stuck to the surface of this billiard ball. So you have a very solid core with these tiny little pieces stuck to it. This model was called the Plum pudding model. After the model was developed, another person came along, an American by the name of Robert Millikan. And Robert Millikan worked to determine the size and the charge of that electron. The experiment over here at the left is called the oil drop experiment. In the oil drop experiment, the basic idea is that a tiny stream of oil particles were sent through a charged zone. And that charged zone would give those oil particles some type of attraction. And by measuring the amount of distance that the oil particles moved in relation to where they should have gone, a charge was devised and a mass was devised. And though he was slightly off, eventually Robert Millikan's work led to the discovery that an electron is 1/1840th the size of a hydrogen atom. He was also able to figure out the precise charge of an electron to be 1.6 times 10 to the negative 19th coulombs. For our purposes, though, that's a very, very tiny number. So what we consider is we can call the charge of an electron a -1 charge. Early in the 1900s, somebody else jumped into the game. Someone who didn't believe in the billiard ball or the plum pudding model. His name is Ernest Rutherford, a very influential figure in science. Rutherford devised an experiment in which he could shoot tiny little particles called alpha particles at a piece of thin gold foil in what's become called the gold foil experiment. Gold was chosen because it's a very, very dense metal. In fact, it was one of the densest metals known at that time. It could also be pounded into a very, very thin sheet. Rutherford actually believed he was pounding that thin sheet into a single layer of atoms, and he wanted to test the model of the atom to that point. Now remember, at that point, we had the whole billiard ball and plum pudding model, where we had a solid sphere. And so what he believed is that he was lining up these gold atoms. And as he lined up these gold atoms, he figured if he shot a very tiny charged particle, an alpha particle, with a positive 2 charge, at this wall of gold, right here, that it should go through undeflected. His results were quite staggering. So again, he believed that most of the time it would hit that particle and bounce back because it was a solid core. What he found, though, is that most of the time the particles would fly straight through, undeflected. Every once in a while, a particle would fly in and slightly change its angle. Very few would hit and radically change their angle, and then even fewer yet would hit the gold and actually bounce back. And so what he came up with was a different idea. He'd observed thousands of attempts at firing into this gold foil. Think about throwing a tennis ball at a wall. That's really equivalent to what the model was similar to. Now, if you threw a tennis ball at a wall 1,000 times, you would expect it to bounce back 1,000 times. It's exactly what Rutherford thought. Instead, what he found, though, is that most of the time it actually flew through the wall, and very rarely did it actually deflect back. So what he postulated is that most of the space of an atom has to be something that allows a charge through, allows these tiny particles through. And so he developed the idea of the nucleus. And the nucleus was a very, very dense central core. And that central core contained a lot of mass. The rest of the atom was empty space. It made up the entire volume of the atom. Think about placing a baseball in the center of the Georgia Dome. The rest of the Georgia Dome itself would be the empty space that makes up the size of the atom. The solid, dense core of the baseball would be the nucleus. Rutherford set about, after developing this model, to finding that positive charge. And after repeating through J.J. Thompson's experiment using the cathode ray tube, Rutherford discovered a positively charged slow-moving particle. And that positively charged slow-moving particle he called the proton. Working collaboratively with Rutherford on certain organization of different atoms known to man, another guy came along in 1932 by the name of James Chadwick and mathematically calculated out that there must be a third subatomic particle. Now, we have the electron, and the electron had a negative charge. The proton was found to have exactly the same charge, but in the opposite direction, and is given a positive 1 charge. The neutron, on the other hand, was found to have 0 charge whatsoever. The neutron was given a mass product, and is also found in the nucleus. So we can actually say that the proton and the neutron have about the same mass. What I'd like you to do for tomorrow is, using the internet and other sources that you can find, I'd like you to create a table and bring it into class. And in that table, you should have the proton, neutron, and electron classified. I need you to give me their symbol, as I've given you here. I need you to give me their mass, that's actual and relative, their charge, and their location in the atom. That's all I have about atomic theory. Please bring any questions you might have into class tomorrow for our discussion.